So our next topic is the numerical solution for the linear algebra equations. Okay, numerical solution of linear algebra equations. And we talked about linear algebra equations before, back in probably like 1.5 months ago. And that time we were solving the linear algebra equations analytically. Now we want to solve it numerically. Why we want to solve it numerically? The numerical solution of large system of linear algebra equations is a direct consequence of FD or FE method. So as we talked before, we have finite difference method, which we, instead of writing the continuous derivative of your ODE, we write as linear algebra equations on different mesh points within the whole domain. The FE method is also, this whole domain will be divided into different small elements. In the small elements, we will use algebra equations to represent those small domain, then ensemble that into the whole domain. So if your system is very complex, and also if your system has a very fine mesh, you can imagine your system will have a huge number of the linear algebra equations to solve. Then if you just use Gauss elimination, that can be an issue because you couldn't solve it. So this topic, we will talk about what kind of numerical solution we can use for such large system of the linear algebra equations, okay? For solving ODE or PDE, okay? PDE represent the partial differential equations, which we will talk at the end of this class. Okay. So there are two numerical solutions we want to introduce for numerically solving the linear algebra equations. The first one called the direct elimination method. And one of them we've already talked before. It's called Gauss elimination. Gauss elimination. Okay. And we will talk more detail regarding the LU decomposition. Okay. So that is called direct elimination method. Another one is called the iterative method. And that is for large system. So the Gauss elimination, as we introduced before, can be analytical solve the linear algebra equations, but that is only for small system. LU decomposition also small or mid system. For large system, the iterative method will be the most efficient for the programming, okay? And then let's recall what is Gauss elimination. Probably you all know, but let's just refresh our memory regarding the Gauss elimination. So we are solving AX equals to B, this system, okay? And we are trying to solve the X, which is non-trivial X. And how we solve using Gauss elimination? We first will construct an argument matrix, which is a argument matrix, which is A, B, okay? After we construct our argument matrix, what we need to do next. So the next, we need to convert this argument matrix using elementary row operator. So elementary row operator. Convert our argument matrix into an upper triangular matrix. Upper triangular matrix. Right? After we convert our upper triangular matrix, what we need to do next? We need to do back substitution to solve all the x in the vector of x. So we need to do back substitution to get our final x. And what is the computational expense we mentioned before for the Gaussian elimination? So for the upper triangular, the computational expense is on the order of n to the third, which is n by n matrices. Okay. And when you do the back substitution, that is on the order of n to the 2. So overall, the Gaussian elimination computational expense should be n to the third. Okay? Because when your n is super large compared to n to the third, n to the second is very small number as compared to n to the third. So the disadvantage, we talked one disadvantage for Gaussian elimination before, which is computational expensive. Computational expensive. We also notice for Gaussian elimination that we have to know what is the B part. The B has to be known in order to build the argument matrices, in order to have the back substitution, right? So the B has to be known. So this is the Gaussian elimination directly solve the large system of the linear algebra system. Disadvantage is the computational has to be very expensive, which is n to the third. And the B part has to be known for Gaussian elimination in order to solve it.